All right, so we've got a new topic today. So we've moved on from torsion, and now we're going to a one-day topic called thin-walled pressure vessels. So these are thin wall, meaning that the ratio of their wall thickness to however big around they are is small. We'll talk about the numbers later, but they're pressure vessels, meaning that in general they have a higher pressure inside them than outside. I guess they could be the other way around, like a vacuum pressure vessel where it's lower inside than outside, but this internal pressure puts a strain on the walls. And we're going to assume for our class it's going to be a higher pressure inside, so it's wanting to blow the pressure vessel apart. And so we need to be able to calculate that stress so that we can make the thin wall pressure vessels sufficient to deal with whatever kind of internal pressure might be put inside them. This could be like a Coke can, basketball, airplane fuselage, when it's in the sky anyway. Something like that where it's a round, could be sphere, could be cylinder for us. They technically could be any shape, but they kind of have the same issue of the as the shafts, where yes, you could make a rotating shaft some shape other than a circle, but then you have issues that you have to that complicate the analysis of it and complicate the strength of it, compromise the strength of it. So these are going to be sphere or cylinder. We're not going to really consider the effect of what the ends might be, because like a Coke can end, they're kind of flat, and the airplane end are kind of pointed, and so there's different types of end caps that could be on the pressure vessel. We're not going to get into all of that part. We're just going to spend one day, a few minutes talking about these pressure vessels. So why don't we, let's just first go over here and recap where we're at. We're close to the end. We have this topic and one more. So Friday we'll have stress concentration factors. And then next week is no streams, but we'll be doing our exams. So Monday, either exam 1 or 2, redo. You can't redo both exams. You pick one of them, and you will have both of them available at noon, both of them available at 7 for the Zoom proctoring. But you can only do one. Once you start one, that's the one you're doing. And whatever grade you get, that replaces the old grade. If somehow you do worse on the retake, then, well, that replaces your original grade. Very, very, very few, if like in the less than 5 people over 20 years have done worse. And even those that did worse, like 1 point worse or something, basically they did the same. Most people improve their exam grades 5 to 10 points, some way more depending on how badly the one they're replacing was, how badly scored it was. But that'll happen on Monday. Wednesday will be exam 3. Exam 3 covers all of the topics, I think. Let's see, let's make sure. Yeah, there's an outline. This outline's from 2020, but it's the same basic outline today. So there's an outline of kind of what to expect, but it does go all the way back to the very first thing we did with just force resultants, 2D equilibrium type things, and then goes all the way through what we'll do Friday with the stress concentration factors. We have done things like, some SolidWorks type of questions, assignments rather. There might be a question about finite element analysis, but there would be no finite element analysis problem. You don't have to actually solve anything. You don't have to go into SolidWorks and do any kind of simulation or anything. There might be a question about terminology. That's possible. But that would be it. Generally, the exam is somewhere, and it's not exact, but somewhere in a third of the questions go back to exam 1, a third in exam 2, and a third are these new things, which are torsion, stress concentrations, and thin wall pressure vessels. And that's it. Then we're done. There is one more day in the quarter, so August 15th, that Thursday. But all I've got there is that's just the last day to get stuff done. So web work will, be finished then. Any of the group reports. I did get an email um, about trust project teams. So the ideal number of people is 3 or 4. If you need something outside of that ideal, you'll have to send me, why do you need something outside of that ideal number? And I'll reply to it. I think there is one email I haven't replied to right now. But that's kind of what's coming up. Today should be a pretty short day as far as content goes. Now, if you have questions about other things, then we can try to answer some of those. We'll also have question time on Friday. Let's see. What do you mean by it's finite? So the SolidWorks, the Lab 1, Lab 2, and then the trust simulation, those are finite element analysis. If you had a test question on exam 3, you would not have to go break out SolidWorks and run anything. It would be something like, I don't even know what would be a good question, but it would be a concept question, like something about the elements themselves, or what is a mesh, or something. I don't even know that they're. I'm just saying that you don't have to get SolidWorks out and work any problem. If there's anything at all about SolidWorks on the exam, it would just be a fill in the blank question. So that's, let me see if I even put that on the outline here. So that's why I said that, because on these content questions, the word finite element does show up here. And that would just mean that if there was anything about SolidWorks, it would show up in those fill in the blank questions. There wouldn't be a reason that you'd need to solve anything in SolidWorks simulation. That's what I mean by that. And again, these are not, it's not necessarily that there will be one question on this, one question on this. There will be something like this. This is similar to the level of types of questions. So again, the fundamental questions, those are usually like 1-step things. The BC level things are maybe 1 or 2 steps, and then the challenging ones, there's, you're designing a problem, a solution, trying to figure out the wall thickness of a pressure vessel or something. It's more of you're integrating more topics into one question. So there's kind of the outline. Again, well, actually this says 2019, but still, it's the basic. This course doesn't change much over the years. It is what it is. All right, let's get into our topic for today, and that topic is thin wall pressure vessels. It does have a homework that goes with it. It should be open. It's going to stay open until the 15th, I believe, and I think it ends at like 2 a.m. on the 15th. It'll stay open until then. All of the homeworks that are open now, I think that's when they end. So let's look at thin wall pressure vessels. All right. Oh, I didn't. Okay, good. It's not. We're not gonna have to reset the monitor today. All right. So the first part is like the first word here, thin walled. So when we say the wall of the pressure vessel, we mean like if it's the Coke can, it's the metal part, right? If it's the basketball, it's the rubber and leather part. So it's the wall of the pressure vessel, and we have to specify that these equations that we're going to develop, we'll end up with 2 equations. They are specific for thin-walled pressure vessels. So there are thick-walled pressure vessels that develop their stresses differently than what ours do with thin wall pressure vessels, and they're not part of this topic. So thin wall, there can be a couple of different ways you might define thin wall. We're going to say that the variable t, lowercase t, that's the wall thickness. And for us, then I'm going to put approximately, but it's going to be less than 10 times the radius of the pressure vessel. So you might see some other ranges for what constitute thin wall versus thick wall pressure vessels. This is the one we're going to use. That could be a concept question, I guess, but it's not going to. I'm not going to try and trick you with giving you a thick walled pressure vessel and then tell you to solve something about it, and the answer is that, well, these equations don't work on thick wall. So don't worry about that, but just realize that there is a difference for the equations in thin wall and thick wall, and you'll see that shortly here of why we have to limit these equations to working with thin wall pressure vessels. Okay, we are going to use two. So one of our pressure vessels is just going to be a sphere. So this would be more like a basketball. So something where the wall thickness is still less than about, somewhere around 10 times the radius. It's less than, wait, did I write that right? That's not written correctly. The wall thickness, no, obviously the wall thickness is less than 10 times the radius. The radius over 10, I think it would be a more sensible way to write that, wouldn't it? Because that would, the radius times 10, yeah, the wall would definitely be thinner than that. So the wall thickness would be less than a tenth, 1/10 of the radius. That would be a better way to write that, wouldn't it? So somewhere in that range, and it's not an exact threshold of when you switch from thin wall to thick wall. Probably whatever industry you're dealing with, is this the chemical industry and these pressure vessels are some kind of chemical tank or whatever, there's probably some standard for what your application is. In general, the wall thickness needs to be somewhere less than a tenth of the radius. That's somewhere in that range. Okay, so we're going to have spherical pressure vessels, so basketballs and stuff like that, and we'll have cylindrical ones. And I already said, oh wait, I don't want to, more like that, that we are going to only have, or we're not going to worry with, rather, the end caps on these things. So it is possible that these might have spherical end caps, or they might have, that looks hard to read, let's erase this part. They might have flat end caps, more like a Coke can, or they might have rounded end caps. They might have concave end caps, all these different types of things depending on what the pressure vessel is. We're going to put all of those in our cylindrical category. And we're not going to really, as part of this course, look at the effect of what the end caps might do. All right. So how we're going to do this is we're going to cut open. We'll start with the sphere, and we're going to cut this thing open kind of through a diameter. So we could cut open through here somewhere, like a little sliver off of the sphere. If we did that, we wouldn't be analyzing the worst case stresses in the wall of the pressure vessel. So those do exist. You could do that. But normally, you want to find the worst case scenario, and that's going to be if I cut through a diameter. Now, it does not matter if the diameter is vertical or some other diameter. Doesn't matter, because for a sphere, it's all going to look the same. So I'm going to draw one that's as if I cut straight down the middle of the sphere vertically, but it can be oriented whichever way you want it to. So what that would do is it would give me this kind of free body diagram. So let me try and draw something, not green though. Maybe like that. And then let's make a bigger one. Something like that. And then we need a circle. Maybe like that. Okay, and then we'll erase this part. So there's our cutting through the center of this thing. Now, like I said, you can cut any slice you want to, but the worst case stresses, wall stresses, are going to be if I cut through the diameter. So the stresses I'm talking about, they are in the wall here. So I'm going to draw a few of them, but recognize that this is a wall stress that's all around the wall of the pressure vessel. I just don't want to draw that many arrows. And we're going to call this sigma A. A because it is an axial stress. It'll make more sense in the cylindrical pressure vessel where there is a longitudinal axis versus a sphere where kind of all the axes, they all look the same. But we're still going to call it sigma A. And it's the stress in the wall of the pressure vessel. It's a tensile stress. Assuming I'm have a higher stress inside than outside, then that's going to put a tensile stress in the wall of the pressure vessel, wanting to explode it, blow it apart. I'm going to use a different color. We'll use the purple one here. And I'm going to draw one large arrow here just to, again, to save some space. But this guy I'm going to call P, and it is the internal pressure. And then we already defined a variable T. I'll put it over here, I guess. Make it go further. Now, the way I drew it, you know, it looks like some of it's thinner and thicker. It's all the same size, just as part of the way I drew it, I guess. This internal pressure works on, I'm going to make it, I think, pink. Works on a surface. So there's some kind of fluid in this thing. It could be air, or it could be a liquid type of fluid, or whatever. But what we're imagining here is a some kind of fluid-filled chamber here, and this internal pressure P is the pressure from this fluid, and I'm showing it trying to blow this left half of our sphere away from the right half of the sphere. And so I'm showing the pressure going to the left. And then I'm showing the stress in the wall holding it all together going to the right. So I can do a balance on those stresses and pressures, actually on the forces that are causing those stresses and pressures. Let's make the wall, let's make it green. It's going to get really crazy colors here, but that's okay. So this little green ring is representing the area of the wall that's holding everything together that has this sigma A wall stress applied to it. So if I can't just do a pressure balance necessarily, but I can do a force balance. Like, well, that's what we've been doing, a summation of forces in X or Y or whatever. And I can say that this thing's in equilibrium unless it is blowing apart. And I can do a force balance. So if I can figure out the forces associated with these pressures and stresses, then I can do that force balance. So, well, we need one more variable. We need, let's see, maybe I can make that in blue. I don't know what color it's going to come out. Yeah, kind of a dark blue. That's the internal radius. Okay. So R in our equation is going to be the internal radius. So there is some thickness to the pressure vessel. So R is not the outer radius. So it is the internal one. That could make a difference. You know, if you're at the upper limit or of how thick the wall is, then maybe it does make a little bit of difference on internal versus external radius. But if it's something like a Coke can, the wall thickness is super thin, and so the internal radius is very close to the same number as the outer radius. All right. We want to do a force balance, but I have pressures and stresses. So we go back, this is like week 1 or whatever, where we said that stress equals some kind of force spread out over some kind of area. Pressure is the same way. So pressure, they even have the same exact units. Pressure is some kind of force over an area also. We usually use stress for things that are internal to a, we've been using a metal, but it could be other materials, some kind of internal stress that develops whenever you try to pull on this thing or twist it or, well, bend it or whatever. This would be more like an axial, trying to pull it apart. And we use pressure more for when there's a fluid that's compressed in some way, and it has a pressure associated with it. But they're the same units, same idea, force over area. So if I know that a stress or a pressure is a force over area, and I have a wall stress and an internal pressure, I have those things, then I should be able to figure out the associated force, at least an equation for the associated force. So let's go maybe here. Sigma A, remember that's the wall stress. That would equal, based on the idea that, well, a stress equals a force over an area, it should be the force in the wall divided by the area of the wall. Okay? And for P, the internal pressure, so same idea, pressure is a force over an area. It should be the force from the pressure, or the internal, I don't know what you want to call it, but we'll call it the force from the pressure, divided by the area that this force is acting on, so the pink area in mine. So I'll say that one's the pink one, and this area of the wall is the green one. Okay. So let's I wrote them as sigma A first, then P, but let's actually work on the P first, the internal pressure. It's a little more straightforward, and then we'll do the wall stress. So let's say that I think I will use F sub I actually for the internal pressure. Do I need to use, well, we can use F sub P, that'll be fine. Since I wrote force pressure, we'll use F sub P. So all I'm doing is rearranging the equation. F sub P equals P, the internal pressure, times the area of the pressure. This is also, remember early on I said that you could do, some other slice, but now my area that the pressure is acting on is smaller and smaller, and the wall thickness is different. It's a different area. So these areas would change, even though the pressure itself wouldn't change. So if I wanted the worst case, I need to cut through the diameter. So I could make this a little bit more equation-like and say that Fp, so the force from the pressure, the internal pressure, equals P, the internal pressure, which I usually know. Like, either I'm trying to solve for how much pressure can you put inside the Coke can before it blows up, or I know the internal pressure, I want to store 250 psi, how thick do I need to make the wall, or what material do I need to make the wall from? So I usually am either trying to solve for P or I know P. And then the area, looking at my equation or my diagram here, the pink area, I have the internal radius r, and it's just a circle, so pi r squared. A lot of times I use diameters instead of radius because it's easier to measure a diameter in general. But in this case, these equations, we do use radius. So we're going to use a radius. All right, so that's pretty straightforward. It also shows, that r is the internal radius here. So that is when we are solving for this pressure that we're going to, or these wall stresses or whatever we're solving for, it is the internal radius that we're dealing with. So the green area, so it looks like what you would do is this. I'm looking at it kind of head on now, so instead of the ovals, I'm going to have circles. So let's center that guy up. So we had it green, right? So here's our, I drew it a little smaller, but that's okay. Here's our wall area, and the stress, the wall stress is acting on this area. I wish there was a fill button where I could just fill in the areas here versus coloring them in. Maybe there is, I don't know. We'll do it this way. We have that internal radius R, and we have the variable sigma A, we have that. So what you would think you might do is, well, the area of the wall is equal to something like, pi outer diameter squared over 4 minus pi inner diameter squared over 4. So assuming you knew that, or you knew one of the diameters or radiuses and the wall thickness, then you could figure out the area. That's true, but it's not how we're going to do this. So this is what makes this a thin-walled pressure vessel versus a thick wall. We're going to say that in the case of the thin-walled pressure vessel, the stress in this wall is pretty evenly distributed because the wall is relatively thin. If I had a thick-walled pressure vessel, then yeah, the stress wouldn't develop evenly across the wall. Like, it'd be one pressure or one stress close to the inside and a different stress close to the outside. But since the walls are so thin, then it's pretty much the same stress on the outside surface and the inside surface. And so even though I could calculate this equation, and it doesn't look like it'd be that difficult to do, we're going to not use that equation. Instead, what we're going to do is we're going to pretend that we slice this little ring, this green ring, and we lay it out flat. Whoa, that's not what I intended. Let me try that again. There we go. We lay it out flat, something like that. Let's center it up. And, if I were to slice this thing and flatten it up, let me move this out of the way, so that I still have the same area, more or less. I've just turned it into a rectangle. So it's kind of like this is a sphere, but maybe you can envision it better if it was a cylinder. So I took it and I flattened it all out. And now the dimensions are this dimension, which is my wall thickness. We just call that T. And this dimension and this one is it's the length, but it's also the circumference. So the circumference is pi times diameter, but we are wanting to use that radius. So instead of pi times diameter, we're going to say pi times 2 radius, so that we get that R in there. And this is still the internal radius. So this part only really works when it's a thin wall. If this were a thick wall, then taking it and splitting it apart like this would get less and less of a good approximation for what's going on there. Plus, the stresses would be more unevenly distributed in the thickness of the wall versus it being a thin wall. So if I make this approximation, now what I called the area of the wall equals T times 2 pi R. Okay? And going back to my equation up here, this equation, going back to that, I can plug in, well, sigma A equals the force in the wall. Well, actually, let's do the force in the wall equals, instead of writing it that way, force in the wall equals sigma A times the area of the wall, which my approximation for the area is T times 2 times pi times R. Now I have two equations here. I have this equation and I have this equation. Not sure why sometimes it makes nice squares and sometimes it does not. There we go. I guess it's how closely to a square did I draw it. Both of those are forces. One of them is the force associated with the internal pressure, and the other is the force associated with the stress in the wall. Those oppose one another. If we go back to here, you know, the force associated with the wall stress should be going in the same direction as the stress in the wall, the little red arrows. The force associated with the internal pressure should be going in the same direction as the purple arrow. And so those are opposing one another. So I should be able to write a force balance equation. In this case, it looks like I drew them in the x direction. So summation of forces in the x direction equals 0. I had the red wall stress going to the right, so I'll give them the positive sign. And so that would be F wall minus F from the pressure, which because I had it going to the left. Those need to add to 0. If they don't add to 0, that means the thing is exploded. I guess it could mean that they're imploding, but it's not in equilibrium. And I have equations for both of these. So if I substitute in, well, the force in the wall is sigma A times T times 2 times pi times R minus the force from P, which is P times pi R squared. I could solve this equation for whichever variable I want to solve for. So normally I am calculating the stress in the wall because I want to make sure that I don't exceed the strength of the material. So normally I want to isolate sigma A. So if I do that, that would mean moving P pi R squared over to the other side and dividing by T2 pi R. Sigma A equals P times pi R squared divided by T times 2 times pi times R. Pi cancels out. R cancels one of those R's. And I'm left with sigma A equals PR over 2T. So this equation will calculate the axial stress in the wall of a thin-walled spherical pressure vessel. So that's what this does. And maybe we won't use axial. Let's use normal stress. In this case, maybe it's hard to think about an axis, longitudinal axis when it's a sphere because it could be any orientation and all look the same. So let's say that this is normal, meaning that the stress is normal to the surface it's acting on, so the red arrows are perpendicular to the green surface. So we'll call it the normal stress, although you will hear it referred to as axial stress. In the variable is sigma A anyway. But normal stress in the wall of a thin-walled pressure vessel, spherical pressure vessel. Okay, so the equation itself is pretty simple. I wanted to go through the derivation here. One, so that you could see that the R is the internal radius. That kind of comes from the pressure side of things. All right, so I think we're back. For now, let's carry on with the cylinder. So maybe I'll copy our cylinder and go down here with it. So the first thing is, let's cut it this way. Now if I do this, I drew this one a little more obliquely, I guess, but if I do this, I'll get this exact same thing. The back, where I've got a semicircle on the back of it will look different, but the area where the wall stress is and the internal pressure, all that's going to look exactly the same. So this version, wow, why is it, I don't know what I'm doing to make it go back and forth. It does not want to go here for some reason. I don't know why it's doing that. This will give me the exact same derivation. Everything will be the same. And so cylindrical pressure vessels do have this same stress. So you would still have sigma A equals PR over 2T. And it would be the normal. This one, whoops. This one, maybe it does make a little more sense to call it the axial stress, but it's the exact same thing. In the wall of a, still a thin wall, cylindrical pressure vessel. Okay. The thing about it is, though, that there are ways that I could cut the cylinder open and it not all be the same thing. So any diameter that I cut through the sphere, they're gonna all end up looking like this. But there is a longitudinal axis here on the cylinder where if I cut along that direction, I will get a different free body diagram. So we need to look at that one. So let's take, well, actually, let's take this one. I don't want the green line on it. And let's cut this one. I want to cut it this way. I don't know the best way to show it, but it's going to be cutting this direction, but I don't want to draw that body. I mean, I guess I could, let's see. Let's do it. I'm just going to cut it the other direction, but I'm going to rotate it a little bit so that you can see better. So I'm really going to cut more like if I cut a plane like this and I end up cutting, you know, through here. That's what I'm going to draw the picture of. Hopefully that makes sense. Maybe when I draw the picture it will make sense, hopefully. So here's what the picture will look like. Something like this. So I've cut it open, so I don't have, can't see that now. See if I can copy just that piece. Yes. Okay, and I would have cut through this wall. Couldn't see that. This one would be, based on our other diagram, this would be green. And I'd have another wall down here. And then we'd have something like, I don't know, this. Something like that. So the pink area for this one that corresponds with the pressure, internal pressure, that would be all of this in here. All of this. I don't know if I want to color this all in or not, but maybe it won't take too long. So that's the area that the pressure, internal pressure, is acting on. And the green area is the wall area that's holding it all together. So there's a stress in there. This stress is going to be called the hoop stress, H-O-O-P stress. to differentiate it from the axial wall stress. It's still a wall stress, it's just in the other direction. So I'll try and draw, a couple of arrows out here. I'm not sure if this is quite the right angle to draw them at, but you'll get the idea, I think. And this will be sigma H for hoop. Then we'll have the same idea with P. It's all distributed over that pink surface, but I've dropped one purple arrow to represent it all. And we'll do the same thing where, well, the stress is force divided by area. Same thing with pressure, force over area. I just have a new set of areas here. I've got the green wall area, so let's also say we know that this dimension is L. So I've got that same area, and then I've got the pink area, which would be the radius. So here's the radius. There's 2 radius times L would give me the pink area. So let's write out our equations for the related to the hoop stress and related to the internal pressure. So sigma H, the hoop stress, is the force. So the force from in the hoop, I suppose, over the area of the hoop, which it looks like there are 2 of them, times they're each, I didn't write this one, they're each this thick. Remember, this is the wall thickness. So 2 times wall thickness times length of however long the pressure vessel is. And again, we're ignoring the end caps, what they might contribute here, we're ignoring those. And then I've got the pressure, internal pressure, equals the force from the pressure over the area that the pressure is acting over, which looks like it is 2 times R times L. And then I've got my idea of, maybe this is the Z direction, we might say that. Maybe it's the Y direction, whatever direction we want to call this. Summation of forces, we'll call it Z, equals 0. And I've got, let's say that the hoop is in the positive direction. So the hoop stress force is actually F. Well, we got to isolate the force, don't we? Hold on, I might have skipped a step here. Let's move that down. So if we solve for the force, so we can actually add them together, the force associated with the hoop is the hoop stress times 2 times T times L. The force associated with the pressure is P times 2 times R times L. When I add those together, they are going in opposite directions. Let's say the hoop stress force is going in the positive direction. So sigma H times 2TL minus the force associated with the internal pressure, P times 2 times R times L. Same thing, I'm normally wanting to solve for the hoop stress because I want to design this canister to make sure that it doesn't have too large of a hoop stress in it and blow up, something like that. So I'm going to isolate sigma H, and that will move the P2RL to the other side of the equal and divide by 2TL. So looks like the 2's will cancel, the L's will cancel, and my hoop stress equation, sigma H equals PR over T. So this is the hoop stress in a thin-walled cylindrical pressure vessel. Now, we didn't have to make the same assumption about the, taking the sphere and laying it out flat. We didn't have to do that on this one, but it still has to be thin-walled because we are assuming that this hoop stress is nice and evenly distributed throughout the wall of the cylinder. Whereas if it was a really thick wall, then you would have a variation of stress from the inside of the cylinder to the outside of the cylinder. Okay, so if we look at that, PR over T for the hoop stress, PR over 2T for the axial or longitudinal stress. So for a cylinder, it looks like the hoop stress is the one you always have to design for because it is twice the amount, PR over 2T versus PR over 1T. So it's twice as large as the axial or longitudinal stress. You sometimes have to deal with both of them. We're not going to in this course, but you might imagine that this was created by welding a seam across here, and the seam, maybe it was, welded in a helix, and then you might have to combine these two stresses in the real world. We're not going to do that though. We're just going to keep them totally separate, hoop stress and axial or longitudinal stress. All right, so those are our two equations, PR over T, PR over 2T. Let's take to web work and find some of these problems, solve a couple of them, and then if I see any questions for other topics or about pressure vessels, then we'll look at those. Let's see what I have in web work. This is in the optional 3, problem 14. And it's just like a 2-sentence question. So we'll start with that one. Seems probably like it's pretty simple, but let's start with that. All right. Spherical gas storage tank. So like maybe a propane tank or something. Where it's pressurized inside there. It has a diameter of 34 feet, so it's giant. A wall thickness of 0.625, so that's 5/8 of an inch. Determine the maximum normal stress. So they did use the word normal stress here versus axial stress in the sphere. That makes more sense. In the tank, if the internal pressure is 120 psi. Okay. So when we're dealing with sphere, we just have the one equation, PR over 2T, at least as far as maximum stress is going to go. And this course isn't going to try and calculate anything less than the maximum for pressure vessels. So sigma A equals P times R over 2 times T. Okay? They told us the internal pressure, 120 psi. Remember, PSI is pounds per square inch. They didn't tell us the internal radius, so what they gave us is the diameter. They didn't specify if this is inner or outer diameter, but you would think it's the outer diameter. So we have to actually figure out the inner radius. So we'll go over to the side here. OD equals 34 feet. So that means the outer radius is half of that, which is 17 feet. Let's go ahead and convert that into inches, though, since my other stuff is in pounds per square inch. So 17 times 12 is 204 inches. But the inner radius, R, is the outer radius minus the wall thickness. So 204 minus 0.625 is 203.375. Now, is that 0.625 inches going to make a difference in our calculations? For web work, it might. but probably on anything outside of web work, it's probably going to be pretty close to the same answer. So radius is 203.375. So make sure you convert to radius, not diameter, and that you're using inner radius. Over 2 times the wall thickness of 0.625 inches. So this one is just plug in the numbers and calculate. So 120 times 203.375 divided by 2 divided by 0.625. 19,524. The problem is telling me to put it in KSI, so 19.524 KSI. Let's plug that in and make sure we get that done. 19.524. And that's correct. Test 2 grades should be, I would think Friday is probably when they'll be totally done. It would be my guess. Let's see if there's any other web work problems here for sphere. Or so here's a cylindrical one. Let's work on that. All right, so we've got cylindrical now. So now we have the hoop stress and the axial or longitudinal stress, or normal stress, whichever one you want to call it. This one specifies outside diameter, so we do know that the 3 meters is outside. Wall thickness of 19 millimeters, so we have mixed units, millimeters and meters. Hoop stress, allowable hoop stress is 120 megapascals. Allowable axial stress is 55. So we actually have 2 different allowables here. So we can either think about it, or we'll run the numbers to make sure, but you could just look at them and tell, knowing that the hoop stress is twice the axial stress, we could just eliminate one, but we're going to run the numbers. So what's the maximum internal pressure that we can use for this tank? So based on the axial stress for a cylinder, well, the axial stress for a cylinder or a sphere is the same. So the maximum pressure, we'd actually need to solve for P. So P equals sigma A times 2 times T over R. Just rearranging the equation. Sigma A allowable for axial is 55 megapascals. Wall thickness of 0.019 meters. Outer radius, all right, so we have a 3 meter outer diameter. So 3 divided by 2, so 1.5 meter outer radius. Let's subtract off our 19 millimeters. 1.481 meters. So I kept everything in newtons and meters. Remember, a pascal is a newton per meter squared. And this will give us the maximum pressure according according to the axial stress. So let's see. 55 million times 2 times 0.019 divided by 1.481. And it's a big number because these are pascals, what I would calculate. So 1411208.6 pascals. So that's 1.41 megapascals. Okay. For the hoop stress, so this is all axial. The hoop stress, sigma H, is P R over T. So solving that for P equals sigma, that's an H, not an N, sigma H times T over R equals, we're allowed a different amount of hoop stress. We're allowed 120 megapascals. T is still the same. And the internal radius is still the same. Let me make sure those don't look like they are the same problem. There we go. So 120 million times 0.019 divided by 1.481, 1536388.14 pascals. So looks like the maximum here is 1.54 megapascals. So I've got these two, and one of them limits the whole thing. So it looks like the axial stress is actually the limiter at 1.41 megapascals. Now I did round on that, so I don't know if it's going to like this or not. It was close enough. 1.411, a bunch of numbers. So these problems are pretty straightforward. They can get, I guess, a little bit more complicated if you were trying to solve for the wall thickness, T. But even then, it's not that big a deal. So the main thing to remember is that for a cylinder, you have hoop stress and axial stress. And for a sphere, it's just the normal stress, the one that we call sigma A. And there's not a whole lot to solving these. Also remember that the R, the radius, is technically the inner radius, because both times where we calculated that pink area, we used the inner radius. There it is there, and there it is there. It's the inner radius. So on a thin thing like a Coke can, that size probably doesn't really make any difference. These problems, you notice the diameters are really pretty big, 3-meter diameter and 34-foot diameter. So those are pretty large, and it starts to be a difference in the inner radius versus the outer radius, because now the wall can be a lot thicker. So that's pretty much it for thin-walled pressure vessels. There will be probably 2 of these on the exam 3. I doubt there'll be 3 of them, but there probably will be 2 questions about pressure vessels, maybe 2 calculations and 1 question. Obvious question would be something about the ratio of radius to wall thickness. I guess you could have questions about if I gave you some dimensions, is this true or false? It is a thin wall or it's a thick wall. You could have that kind of question, something like that. All right, any questions to put in the chat that we need to do today? We will also have time Friday, Thursday, Thursday, for questions after we talk about stress concentrations too. I don't see anything in the chat, so I'm assuming everybody's good. And like I said, we'll be back tomorrow with at noon with some stress concentrations. That's our last topic, and then we'll be nothing but questions about the exam, and we'll actually take the exams and the makeup exams. You do not have to do a retake. Like, if you're happy with your exam 1 and 2 grades, don't think you have to go and do a retake of either one of them. It's totally fine to just go with what you got. All right, so I don't see any new questions. We'll call it a day. We'll be back tomorrow at noon, and we'll talk about stress concentrations and then any last-minute questions.